Awesome. So welcome everyone to TCS Plus. For those who don't know, TCS Plus is an online seminar. We organize a few talks each semester about the latest and greatest results in theoretical computer science. And we're always looking for suggestions for new talks. So if you think there's a result or a topic which would be of interest to TCS Plus, please fill out the Google form on our website. And today we're super excited to have Tom Gurr from Cambridge, who will be telling us about some recent work on zero knowledge PCP theorems. So, Tom, take it away.
Hi, Dan. Thanks, Ivan, for the kind introduction. So this is a joint work with Jack O'Connor and Nicholas Spooner, and it talks about zero knowledge PCP theorem. And there's a nice illustration here from Quantum magazine that I really like, which captures the essence both of zero knowledge and PCPs in the sense that you have a proof here in blue, which is encoded in a way that reveals zero information about the statement. And the way that you access it is through a local view, through a local window, so you only read a tiny fraction of it. But of course, I will tell you about it in much more detail in a second. And so we typically don't talk much about the process of research. We just present the results. But since this has been an 8 year sort of struggle, and at times we lost faith, and then there was excitement. So I wanted to give you a bit of a glimpse as to what happened, behind the scenes. So, some of the events and dates have been slightly modified to make the story more streamlined, but let's start at the very beginning, which is in Berkeley in 2017. And a much younger version of myself was talking to Nick Spooner. And I sort of wondered how nice it would be if we can show a zero knowledge PCP theorem, right? I mean, in a way, both probabilistically checkable proofs and zero knowledge proofs are this reimagination of the notion of mathematical proof. Both of them are celebrated and beautiful. And, it's very appealing to have such get the best out of both worlds. And Nick being really well versed in literature, immediately told me, yeah, I mean, this is amazing, but it's open since like the work of Kilian and Petrank and Tardos. But a lot of time has passed since they sort of defined this notion, and maybe now the time is right because there's been a lot of developments and a lot of new techniques. Okay, so I was thinking, might be a bit risky, could be a time sink, but let's give it a shot for like 1 or 2 months, nothing more, just to like to see if it works. And Nick was happy to follow. Okay, good. So let me kind of make sense like what's the object that we're talking about. So I'm going to start with probabilistically checkable proofs. And the idea here is that we're getting a proof oracle. So we can think about an NP proof, for example, that the graph is three-colorable or something along these lines. But we encode the proof in a way that we can probe it at a very small number of locations, maybe like in the example here, in only three locations, and still would be able to verify it with high probability. So formally, I'm saying that if I have an instance in the language, let's say a graph which is three-colorable, then I have my verifier which will toss coins, probe constant number of locations, and will accept always. And if the graph is, let's say, not three-colorable, so regardless of what uh, bad proof that somebody will write down, the verifier will be able to catch it with some good probability. Okay. And then the PCP theorem states that NP is contained in PCP log n1. So let me break down what it means. So whenever you have this notation of PCP classes, log n means that this is the number of bits, the number of coins that the verifier needs to toss. And this sort of gives us a bound on the proof length. So you can always think of the exponent of that as a bound on the proof length. And this one here says how many queries I need to make. Okay, so the PCP theorem tells us that you can take any language in NP and encode it in such a way that even though you're only adding some polynomial redundancy, you can verify it by only reading constant number of bits as opposed to reading the entire proof. And this is one of the most celebrated results of complexity theory and theoretical computer science. Now, of course, if you see this for the first time, you might wonder how is it at all possible? It seems like pure magic. How can you check the correctness of a proof without having to read it? But the idea is maybe not so mysterious if we look at it the following way. So, let's go with the example before of three-color ability. So in this case, the concern is if we're only looking, so here, we have a graph, and we want to make sure that there are no edges which are colored monochromatically. So the concern is if you have a graph and maybe only one edge is badly colored, then your probability of catching it is 1 over the number of edges, which is very, very small. And so this looks like a very hard thing to do. However, one can encode the same graph and introduce some redundancy in a way that, if the graph was three-colorable, then the encoded graph is three-colorable. But if the graph was not three-colorable, even if, you can color it perfectly except for one edge, now you will have a great deal of edges which are improperly, that can't be colored properly. And therefore, if you sample one of them, you'll be able to catch it quite easily. And that's what I think Eureka Noor has this nice example that, this is called the jam principle. So suppose you have a piece of toast and you have a tiny amount of jam on the toast, the jam representing the error in the proof. And now, if you're going to take a random bite, you will most likely not sense the jam at all. However, if you take a knife and kind of spread it uniformly, then regardless of where you take your uniformly random bite, you will still be able to sense the jam. So this is what we're trying to do in PCB constructions. And I'll briefly mention, I think PCBs need no introduction, but they're extremely good. They have many, many applications in theory, in hardness of approximation, for coding theory, in many types of probabilistic proofs. And they're one of the maybe small examples that we have in where an object that originated completely from purely theoretical curiosity end up finding some very interesting real-world applications, though I'm not going to talk about this in this talk. Okay, so we covered half. This is PCPs, and now the notion of zero knowledge proofs, and these are kind of fascinating notions of proofs. These are proofs in which we reveal no information at all about the statement other than the validity. So you prove something, you know that a certain statement is correct, but not revealing any information of any kind. And I'll illustrate it with a simple example. So suppose you have two balls, one green and one red, and you have a color-blind person that can't distinguish them. So we want to have a way of convincing the colorblind person that these two balls are really of different colors. And how can we do that without, indicating which one is the red ball and which one is the green one? So the colorblind person could take the balls, hide them behind their backs, and then flip a coin. Just if you get 0, you'll keep the order of the ball, and if you get 1, you'll flip the order of the red and the green balls. And now, if the balls are really of different colors, then the person who can tell them apart could easily distinguish every time. But if they're not of the same color, then all you can do is a random guess, and this is doomed to fail. So this is a way in which you can communicate, you can prove that these balls are different, of different colors, without revealing which one of them is green and which one of them is red. And a funny anecdote is that I've learned of this example from Oded Goldreich, who is famously colorblind. So this is another type of real-world practical application. Okay, so now getting a bit more precise here. So here unlike PCPs, we now have an interactive proof system. So I have a strong prover and a weaker verifier. They are allowed to interact with each other. And then at the end, we need to decide membership in a language L. Completeness and soundness are just as usual as we had for PCPs. And now there is this conceptual question of okay, what does it mean for a machine to learn nothing, to have zero knowledge? How do we capture it mathematically? And a beautiful notion of Mikali, Goldwasser, and Rakov is we can capture zero knowledge by the notion of a simulator. So if you can have an polynomial time algorithm that does not interact with the prover, it does not know the secret information, it does not know, for example, the coloring of the graph, you can still generate the same transcript of the conversation between the prover and the verifier. So you can generate the same distribution. If you can generate the exact same distribution, then this means that you've learned nothing from the prover that you didn't know yourself. Okay, so now equipped with these two notions, all we have to do is to combine them and see what the definition we get. So a zero knowledge PCP, a zero knowledge probabilistically checkable proof, is a proof that exactly as in a standard PCP, you're going to only query, a small number, maybe a constant number of bits of the proofs in order to verify correctness in the language. In this case, it would be, but we want this to be also a zero knowledge proof. So we want the verifier not to learn anything about the statement other than its correctness. So we'll allow the prover, typically the prover, has no incentive to, choose the proof randomly because they can just pick any proof that would work and give it to the verifier. But now we want to also protect the prover, so we'll allow us, the prover can generate some distribution over proofs. And we'll have the definition that we say that the PCP is zero knowledge if we have a simulator. So as I mentioned before, so what is the simulator going to do? So there's a small nuance here, so I want to do it properly. So the simulator, we want to say that given any possible malicious verifier, so the verifier doesn't have to be the one that the prescribed honest verifier. So we want to be able to simulate the exact transcript of the conversation. Now, something to notice here that if the verifier can read the entire proof, then it's not hard to see that whole hopes of zero knowledge are impossible. So it's a fairly simple observation. And therefore, we have to give a query bound saying that, as long as you haven't read too much of the proof, then you can still generate the same local view. And notice that, again, the honest verifier will maybe only read 3 bits, but we want to give a safety mechanism that, even if the malicious verifier that tries to learn something makes many queries, we can still protect it. And just like a side comment, whenever you have a simulator, there has to be some sort of a leverage over what happens in the real world. So in the interactive proof systems setting, typically what we do is we allow this notion of rewinding. So for PCPs, the leverage that we're getting for the simulator is while the PCP itself is a proof that is written down and is sort of like an immutable object. When you have the simulator interacts with the verifier, and it sort of allows to generate the proof adaptively. So, whenever somebody tries to query a certain bit of the proof, the simulator gives an answer. And then if you want to query another proof, the simulator can just generate something else. So this is where the leverage comes. And here, this 2 random variables, like the output of the simulator as a random variable and the transcript of the conversation. And there's actually 3 notions of zero knowledge. There's perfect zero knowledge in which you can generate the exact same transcript. You can relax it a bit and get statistical zero knowledge, where we'll generate something which is a distribution which is close in statistical distance, or you can also have a computational variant which assumes cryptographic assumption and can only fool computationally bounded opponents. But we actually get the absolute strongest notion of perfect zero knowledge, so I will not make this distinction, and we will generate a precise same thing. Okay, so what is the theorem?
A quick question. Just on your previous slide, if if you require the verifier to be honest, like not malicious, then could you make the simulator be non-adaptive? Or
If the verifier is an honest verifier only,
yeah.
um,
Sorry, I don't know
I,
if the question makes sense, but just
no, I mean, it does. It's not clear to me that this would help, but it's a good question. I mean, it's worth thinking about it.
okay. Thanks.
Okay, so just like the main theorem that I want to talk about today is a zero knowledge PCP theorem. If you look at the statement, it looks exactly the same as the PCP theorem, only we've added zero knowledge. And to say what this means a bit more precisely, so what we'll have is that for every query bound, so we were saying we want to have protection against, we know that we can't have protection about from verifiers that read the entire proof, but we can say for any amount of queries that you allow the verifier to make, you can get a PCP where you have perfect zero knowledge against that many query adversaries. The proof length would be polynomial, but polynomial both in the length of the witness and also in the length of the sort of security parameter that you want. So if you want, to be able to tolerate more malicious behavior, you need to pay in the proof length, but it would still be this polynomial. The query complexity is going to be O of 1. This is a crucial thing. It's a hallmark of the PCP theorem. And an important technicality is that the way that the verifier will work would be in a non-adaptive way. So it would just, choose the coordinates at random from the beginning, and it doesn't matter what answer it sees. And the reason why this is important is because this is what allows us to get the constant query complexity, because it allows this machinery of proof composition, which is incompatible with other approaches. Okay, so just quickly, what was known before, so the original work of KPT 97, they defined the notion of zero knowledge PCPs, and they got this polynomial length PCPs. The type of zero knowledge is a bit weaker than perfect. It is statistical zero knowledge. And their query complexity was polylogarithmic. And uh, one thing to notice is that their construction was non-adaptive. It was adaptive, made adaptive queries, and that was the main bottleneck why they couldn't get a PCP type of theorem with O of 1 queries. And then there was a couple of works that tried to get this notion of like to obtain non-adaptivity, but it came at some very big cost to some parameters, either in terms of making some witness indistinguishability type of assumption, or in only having a quadratic bound between the malicious behavior and the honest behavior. And I conveniently made this table so that I can put green squares for all parameters here for this work, where we're getting constant query complexity. This is the first one, polynomial length, it's perfect zero knowledge, and we're non-adaptive. Okay. So that was sort of the statement, and now a quick interlude. At this point, I was talking to Nick, and I was trying to think how do we go about it. So the first start is let's try to understand these previous constructions. And Nick's observation was that pretty much all you can do, or all what was done before, was through this machinery of locking schemes. You can kind of imagine it as a sort of being able to put a lock, an information theoretic lock on your object. And as an inherent artifact of using this type of locking schemes, you lose two things. You lose the perfect zero knowledge, so you can't have this locking scheme and have it in a perfect zero knowledge way. And you're losing the query reduction techniques, that proof composition that allows you to get into O of 1. And so being classically trained, my first question is why not just mimic the classical approach that the PCP theorem was made? And this is where sort of Nick said, let's pin it down and see exactly what breaks if we try to do something like that. So here is a 5-minute crash course on how one constructs a PCP. So the first step is called arithmetization or algebraization. And the idea, okay, so let's take our favorite NP complete problem. Let's say it's a 3-SAT. So we have some 3CNF formula, and we want to know whether there exists a satisfying assignment. Now, the idea of an arithmetization is that we want to take the problem, which is a completely combinatorial problem, and we want to endow it with some algebraic structure, with the hope that giving algebraic structure would help us, we can capitalize on that to get efficient protocols. So the idea is to take this formula, this Boolean formula, and encode it as a low-degree polynomial over a finite field. So what does it mean? So it's actually a very simple thing. If you were taking the simplest way, then you can take a variable x and map it to itself. You can take the Boolean negation and just map it into 1 minus x. If you write down the OR function, then you can write this expression that is easy to check. And similarly for n, so you can go term by term and replace the formula by a polynomial. Right? So for example, suppose this was our 3CNF with these variables. You can just do the replacements as I wrote it, and you're getting this low-degree polynomial, right? And now the idea is that, whenever you evaluate this polynomial on the Boolean hypercube, then essentially you're getting and whether the assignment is satisfiable, this assignment satisfies or not. But you're also now allowed to evaluate it outside of the Boolean hypercube and get this algebraic, determined positions. So this is the first step. We endow it with algebraic structure. And then the second step is to use the sort of like main hammer in the PCP literature, which is a protocol that is called the sum check protocol. So let me explain how sum check works. So, typically we do it in high dimensions, but let's start with the bivariate setting. So notice that before I had an asterisk next to the arithmetization because it's a very simplified version of it. So more generally, we'll get some polynomial coming from a finite field. And let's say that it's bivariate and it has a certain degree. So the way of thinking of the polynomial is you sort of think of taking this k by k matrix, and here this is where you write the actual data that you want. So for example, this could be like the outcome of each one of the assignments. And then what happens outside of it, this is the low degree extension. This is where you evaluate your polynomial outside of so this is the extra algebraic structure that you're getting. And now the goal is to be able to sum over all of this blue square. The idea is think if this one gives you 1 every time an assignment is satisfiable and 0 otherwise, then the sum over this blue matrix would just be the number of satisfying assignments. Good. Okay, so now what would be the PCP? So, it's look a bit equationy, but actually it's a very simple thing. The PCP would just give us the marginal of every line. So what do I mean by that? I will just take this, like, the first line and I add all the elements. I will sum them up, and this would be this value. Sum over the second line. So I'm getting the sum of each one of the rows. And now, if you think about it, how can we check? Now, suppose that the prover is being honest and it really wrote down this polynomial, which is the sum over the x variable. Then what do I need to do? I'm just summing over these k points in the proof, and summing over these k points in the proof would be the sum of this row plus sum of this row plus sum of this row, so we're getting the total sum. So this is a way, and so instead of like summing over k times k, like it's k squared terms, we only need to sum over k terms. So it's a quadratic saving. But now, how do we know that the prover really sent this polynomial or not another polynomial? So this is where we're using the algebraic structure. So what we'll do is we'll choose a uniformly random from the field. So not just a row from the blue data. So maybe, we put this point R. And we'll just check that the polynomial agrees with this value. So I'll evaluate the point here in the proof, and then I will query this point and this point and this point and this point, sum them all up, and check that they're equal. And because polynomials are low-degree polynomials form an error-correcting code, then by the Schwartz-Zippel lemma, it's a fairly standard argument. You can see that if the prover gave a different low-degree polynomial, it will not agree on a random element. So this is the idea of sum check. And maybe the important thing to notice is that we got a quadratic speedup. Like instead of summing over k squared elements, we queried k points and summed them up, and we also queried these points and summed them up. So it's a quadratic saving, but it also means that the PCP itself contains quadratically hard computation. So, if I'm querying this point, I've learned a sum of k points. So this is a piece of information that I couldn't have gotten with a single query. Okay, so this is a quadratic saving, and we're trying to get something which is exponential. So the easiest kind of thing to do is to just go higher in dimension. So if we're going in a bivariate setting, we get a quadratic setting. If we go in a trivariate setting, so now it's sort of, we're comparing a line to a cube. So it's k versus k cubed. And more generally, if we look at number of dimensionality, which is roughly log n, like specifically log n over log n, then this means that we're getting an exponential speedup. So instead of querying this, the entire h to the m, we only need to take something which is the size of h, so an exponential speedup. Now, something to notice is that when you do this over many variables, then it's not enough to just send the sum of one variable, but rather you need to send a bunch of proofs, one for each of the variables, so it gives you this collection of polynomials. But this is not very important for the talk because I will focus on the two-dimensional case. The point is that similarly as with the bivariate case, we have the benefit of, we can do things exponentially faster now, but now the PCP contains a point which is exponentially hard to compute. It is summation of a very, very large number of points. And this is very, very, very far from being zero knowledge. Now, so this is how you build roughly a PCP, and then the disclaimer is that this is a massive oversimplification. There's, this type of arithmetization that is much more sophisticated than needs to go. You need to scale things down to NP. You need to worry about, proof of proximity and robustness and low degree testing. But I will sort of ignore all of this now and try to just communicate one main idea, which is how to get this PCP for sum check. Okay. So now we have an interlude. It's a year later in Berkeley, and Nick came up with a brilliant new paper that gave an interactive zero-knowledge sum check for for interactive protocols. And I was wondering if there's any hope for this to work on PCPs. Nick immediately said, yes, it looks like you're a really good fit, but interaction is really key there, so we'll need some new ideas. So, well, we tried a couple of months before. Let's give it another 1 or 2 months, not get too sucked into it. Okay, and then Nick was starting to explain how things work, and then that's what I'll try to do now. So here's the first attempt or idea. We have our polynomial p, and our goal is to sum over the blue matrix here. So the idea is to now add some random mask. So what do I mean by that? You send another polynomial, which is uniformly random low-degree polynomial, and then the proof, instead of talking about, giving the sum of p, it will refer to the sum of p plus this uniformly random polynomial. Now, if you think about it, what did we gain by that? Now, because we added to each one of the points in the proof a random, uniformly random low-degree polynomial, then the proof is distributed uniformly. So, you can just answer like modulo the constraint of the lines. Like, you can just essentially answer uniformly. So this hides all the information in a fantastic way. However, it does the job way too good because it also will hide the actual value that we seek, right? Because now that we want to know at the end of the day that this P plus R is equal to, we want to know what is it equal to, but this R would just give us some random number. So what we really want is we want to add this low degree polynomial such that if you're summing over the entire blue square, it would amount to 0, in which case, I will sum over P plus R, the R part by linearity would just be 0, and so I will get the value that I want. And this is all nice and well, except for one big problem, which is how do we know that the sum of R is 0, right? I mean, if I could somehow enforce that the sum of R is 0, then we'd be good. But how do we do it? And notice that if you were to write here another, proof for the sum of R, then by linearity you can take the sum of P plus R and take minus the sum of R, and then you reveal P itself. So you can't do that. And so we were very stuck. So, in Nick's work, they did it using interaction, but in the PCP setting, it was really not clear. And after a while, we sort of gave up. So jumping a bit forward, it's the COVID lockdown, 2020. And Nick is telling me, look, I have this amazing new idea for this whole project. It's all about anti-symmetry. At that time, I had my little daughter, Zoe, and I grew this horrible COVID lockdown hair. And I really was so excited. I mean, I think at this point, I realized that this has to work. Like, I was thinking to myself, I'm convinced that the construction, that this idea could make the entire thing go. It's just about figuring out the analysis. So I was thinking maybe once or 1 month or two, we'll finally get it. Okay, so what was this, simple but beautiful idea that Nick came up with? The idea is to have this structure versus randomness dichotomy in a way. So what do I mean? I want a mask such that in a definitional way, it would sum to 0 if I'm summing over my entire domain, my entire matrix. But on the other hand, if I'm summing over a part of it and not summing over all variables, then it will take random values. So what is the idea? So this is exactly the same diagram as before, but instead of giving a proof for P masked by the polynomial R, I'm going to choose some M, some other polynomial M. And what is this M going to be? It's going to be an antisymmetric polynomial. So what do I mean? You take R of xy, and you take minus R of yx. Right? So if you want to evaluate M, all you have to do is you need to query if R at two locations, and you can sort of have M. And what's the benefit of having this antisymmetry? So sorry. So the point is, if you're now summing over the entire domain, over all x and all y, then the order of the variables doesn't matter at all. Right? We're summing over all x and all y, so it doesn't matter in what direction you're doing it. So it's either first columns, then rows, or vice versa. But if you're summing over only one variable, then you're getting something which is seemingly completely non-related. And at that point, I sort of felt that this should do the trick. And by the way, I still believe that it should do the trick, but we got a lot of structure here. So the point is, I'm saying, I'm saying that this is, random polynomial, and then everything takes random value. I'm saying, structure versus randomness. But how is this randomness really distributed now that I've added this anti-symmetry? So let's try to see what's happening. So let's zoom in on the combinatorial part. So before we take the low degree extension, before we take all the algebraic constraints. So this is H. The proof that we're adding looks like a random anti-symmetric matrix here, right? Because we enforced it, R of xy minus R of yx. And if I want to now see what happens, then this is easy to see that this is zero knowledge. You can easily simulate what's happening. The only constraints that you need to take care of is, you need to make sure is, how would you simulate? Whenever somebody is asking a query to the proof, here or here, you will just answer uniformly at random. And the only constraint that you need to make is if somebody asks, a point here and a point there, which are antisymmetric, you need to make sure that you're answering in an antisymmetric way. And the other thing is that, you need to be consistent that if somebody decides to query an entire line, then the proof needs to be consistent with that. But this is very easy to simulate. The problem is that now when you're taking the low degree extension and you're adding this polynomial R, which is antisymmetric, so you're getting this uniformly random antisymmetric low degree polynomial. And that was just too much structure. And we spent, on and off about 2 years trying to understand the exact type of the constraints and we just failed miserably. Okay, so the last interlude. Now we're in work. The year is 2022. So it's already 5 years after. And, both Nick and I were finally again at the same place physically. And Nick was saying, now we're at the same place. What do you say about revisiting this old project? And I was very excited. I had this amazing student, Jack, who was full of questions and full of ideas. And I said, let's try to play with it for another couple of months. We're doing it for so long. Why not? And Jack sort of raised this fantastic question. And the point is that, if we struggle so much with antisymmetry and trying to analyze it, maybe we can sort of just make the construction more random and make the analysis much easier. So what was the idea, right? So what we want to do is we have the polynomial, we have the combinatorial part. So we want to keep the combinatorial part antisymmetric, but somehow we want to take everything which is outside all that algebraic antisymmetric part, and we sort of want to re-randomize it. We want to make it as a random low degree polynomial outside. And this is where one can use the combinatorial non-Stalin sets of Noga alone, which provides us with a way of getting uniform low degree extension of zero. So that does mean you can sort of like imagine that you take you write everything here as a zero, and you outside of it, you're getting a uniform random polynomial. So the way that this works is you take the m that we want. It's again this antisymmetric polynomial, r minus r with the flip of the variables. And now what you're adding is you take this annihilator of the x locations within the systematic part, within the combinatorial part, and also of the y part, and some low degree polynomials of the right degree. And this allows you to get an antisymmetry on the combinatorial part that we know how to analyze. And outside of it, you're getting uniform randomness. So now things are much, much more manageable. So if I'm summarizing the entire construction in the two-dimensional setting, so how does it actually look like? You have the polynomial. This is sort of like counting the number of satisfying assumptions. You send a random polynomial, which would be the mask, and then these two polynomials that one needs for the combinatorial Null-Stalin sets. And from that, you can locally evaluate this mask M that is written here, which is this combination that we talked about. So this is the entire construction. But remember, this is only getting us sort of like quadratic advantage over, querying everything. So what we actually do is we take this higher dimensional, log n dimensional, log n over log n dimensional setting. So, and it would look very similar. So we start with the polynomial, we have the random mask, and then we have a bunch of polynomials that would be used for the higher dimensional combinatorial non-Stalin sets. And then we'll have this stack of proofs that we have for sum check. And we'll have this mask, which looks again like anti-symmetry, but notice that here now flipping x and y now amounts to just changing the order of summation from 1 to m into m to 1. And these are just the combinatorial non-Stalin sets polynomial. Okay, and now I just want to mention that this is nice, we have the construction, but in fact, most of the work that was done in this is in the analysis, in the proof that this is indeed zero knowledge. And I wouldn't have enough time to go over that, but I just want to give a hint of what's going on. So what we're going to do is we're going to have the following simulation strategy, right? Like the idea is that we put so much randomization so far. So with the simulator, we'll look at M. It needs to simulate any query. Let's say query here would be one of these stars. So at any point, it would just choose a uniformly random object. And the idea is that the only time in which it would use the power of the simulator to adaptively give answers would be whenever we're reaching one of the constraints. So what are the constraints? For example, constraints could be the summation over a line, which is what the proof polynomial should give. Or if you're looking at the higher dimension, it could be the summation over a plane. So this is one type of constraint. And another type of constraint could be the one that happens when you have a low degree polynomial. Because a low degree polynomial, for example, it satisfies a lot of constraints. It is low degree on lines, it is low degree on planes, it is low degree on algebraic curves. So you need to take care of all of that. And the way that we do it is by proving new structural results about how the Reed-Muller code, the code of low degree polynomials, and the Reed-Muller code augmented with these subcube sums that the sum check polynomials give. And this is, if you read the paper, this is where, 80% of the work is being done in having this algebraic understanding. Okay, so before I conclude, there's a little outro. Now we're in beautiful Cambridge, 2023. And we got this sum check, and if you get sum check, this means that you can get this sharp P PCP for sharp P, and this was the first paper. And at this point, I was saying, okay, this is amazing. The rest should be fairly routine. We just we go from sharp P into NX, then we're going to scale it down to NP. And now, because things are non-inductive, we'll use this like proof composition where we'll make the PCPs robust and we'll have PCPs of proximity. So, within a month or two, maximum, we will have the full theorem. At this point, neither of my co-author was convinced. But 2 years later, here we are. And I want to conclude by just mentioning two open problems. One of them is sort of a sane open problem, and the other one is a bit more, wild. So I'll start with a conservative one. So the question is, so far what we've done is we've matched the PCP theorem that was proved in 92. However, since 92, there's been a lot of work on construction of PCPs. We can make them not of polynomial lengths. We can make them, of nearly linear lengths. We can have very high soundness. We have we have a lot of optimization of parameters, and we can get much, much stronger PCPs. And so far, we've only matched what was done in the original PCP. So the question is whether we can do it. Or even more interesting would be like if you think about the construction that we've just seen, this is a construction where we've really built in a very white box way a zero knowledge PCP from the very beginning. What would be interesting is if you can take off the shelf a construction of a PCP and sort of as a black box endow it with zero knowledge, somehow mask it as opposed to constructing it to be zero knowledge from the ground up. If you can do that, then you can get, the match the state of the art. And maybe the wilder one is the quantum PCP conjecture. So I think this is one of the most important open problem in quantum complexity theory, where essentially one wants to construct a quantum PCP. So you take a QMA complete problem like the K-local Hamiltonian, and you want to be able to have a proof that is locally verifiable. And my feeling is that there's a fundamental problem with like the standard way of constructing PCPs in the quantum setting, which is like very simple to see from the axioms of quantum mechanics that you cannot have a local correction. So you can't make a small number of queries to a quantum code and be able to learn the value of the assignment. So in a way, unless you're reading almost the entire oracle, you can't expect to be able to decode the assignment. So think about, if your PCP oracle kind of encodes maybe a three coloring or a satisfying assignment of a three sat, then you cannot query it in a small number of places and learn something about the assignment. This caused a violation. And now the beautiful thing is that with a zero knowledge PCP, this doesn't happen. And in fact, there is a very nice work which showed that the notion of zero knowledge locally testable code, which is very closely related to that, implies like dual distance in the quantum CSS codes. So there's a very intimate connection between these two notions. And the hope is that maybe this would shed some light and give a potential new direction. Okay, that's all I want to say. Thank you for the attention.
Awesome. Thank you, Tom. So I'm going to pause the recording and then we can take a few questions offline.